So the other type of interference pattern that we're going to talk about is the diffraction grating. And a diffraction grating is basically a multiple source type of interference. The principles are the same. It still uses diffraction, it still uses superposition to build up this interference pattern, but it has a number of differences. One is, well, basically a diffraction grating is like a tiny piece of plastic or glass that's got like masses and masses and masses and masses and masses and masses and masses of tiny slits on it that work like a point source. So there could be up to 6,000 in a centimetre. So we're talking very, very, very close together and very, very, very thin. And that leads to some really interesting things. The first one is we can no longer use our approximation for reasons that will become clear shortly. So first, when you're talking multiple source or diffraction grating interference, the slits are very, very, very thin. And because they're very, very, very thin, the width of the slit is comparable to the wavelength of the light. Therefore, there will be a large amount of diffraction. Therefore, the interference pattern will be really, really wide. You'll get like a massive, big, almost 180 degrees interference pattern because of it. Second, because the slits are very, 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 very close together, the fringes will be very, very, very widely spread. And it's not just because, like, you can just remember it that way if you want. I like to think, well, actually, because there's lots and lots and lots and lots of point sources and they're all overlapping, and I'm not going to draw it because my chief objection to interference is not even so much that it doesn't catch fire or blow up like my favourite areas of science, but that it's really, really, really awkward to draw. But I want you to imagine like there's like, 300 point sources and you have to draw all the interference patterns for them. And you see that out here, the places where you get constructive interference are incredibly widely spread. And because the third difference is that because the fringes are or because there's a lot and lot of slits, the fringes are really bright. There's a lot of light getting through them. Okay, so a diffraction grating has those key differences, and we can no longer use our approximation. So when we solve mathematical problems for the diffraction grating, we actually have to use the angle that it makes. So this is for bright fringes, where n equals 0, 1, 2, and so on and so forth. D, as always, the distance between the slits. And this sine theta, that's the angle between the mid position and the fringe position. So it's this little angle here that I haven't drawn on, but you know where it is. D is interesting. Sometimes you'll get given, instead of the actual distance of, say, however many micrometers between the slits, you'll get given n, the number of slits per centimetre, and you'll need to figure out d from that. So you'll sometimes have to do d equals 1 over n. If there's like 300 slits per centimetre, you can work out what d must be from that. So diffraction gratings, chief things to remember, okay? You can no longer use our approximation, you have to use this formula. Because the slits are very, very, very thin, there's a wide angle of diffraction. The interference pattern appears across a wide angle. Because the slits are very, very close together, the pattern is spread very, very, very wide, even wider than I've indicated here with my little marks. And because there's lots and lots of slits, the pattern is very, very bright. The fringes are very, very bright.